Good afternoon, it's me again, Jean-Louis Van Bellen. I'm a bit of an amateur physicist, or, well, I like to call me an independent researcher. I've been wrapping up some loose ends after, I published, well, two YouTube videos on my nuclei models of nuclides, isotopes, all elements. So I decided actually to revisit, because in these matrix mechanics, pretty complicated mathematics, the concept of self-energy came up again, and that's something that pops up in, my analysis, geometric analysis of the anomalous magnetic moment, that tiny anomaly in the magnetic moment that is experimentally measured, and it usually goes for one of the best measured and theoretically explained quantities in quantum electrodynamics. So let me get on with it. This is sort of a bit the model. It's kind of strange. I have here an image that you can Google where an electron is actually, in most textbooks, the magnetic moment of an electron is explained by some charge going around and around with a certain velocity. We think it's light speed or near light speed, because we like to think of that charge as a naked charge with no rest mass. And then you can see it has some angular momentum L and some magnetic moment. The opposite directions of the current I and the velocity are just because of the convention that charge, that a current is a current of positive charge. So if you have a negative charge, then it goes in the other direction. So what everyone found, and it's sort of the basis of quantum electrodynamics after the Second World War, is that, if it's really like a point, like infinitesimally small charge that goes around and around, and you get a theoretical magnetic moment. And the real magnetic moment, as measured in penning traps, is very, very different, about 1% difference. So Julian Schwinger calculated that tiny correction based on what is now known as a one-loop correction based on an exchange of virtual photons between charge. I'll come back to that, I'll show that. And I said, yes, this correction is supposed to be one of the most precisely verified predictions in mainstream physics. But where does the number come from? I said main standard textbooks will present this image, but then at the same time say sort of, they're virtual photons that sort of ghostly pop in and out of existence, out of the vacuum. We think the answer is much simpler. We think it comes from the electron's own geometry, that motion that we show here, but we do not assume that a particle or a charge, if you model it as a sphere or a shell or whatever, has no size whatsoever, and it's that tiny size that we think is of the order of alpha times the Compton radius of or the interaction radius of an electron as a whole. That comes from there, and the fields that are generated by that non-zero size point-like charge. So we want to show you how to solve this mystery. Showing using nothing but, indeed geometry, relativity, and really classical field theory, just old classical electromagnetics, Maxwell's equation, no virtual particles, no renormalization, just physics that you can visualize. So this is the publication I updated today. It was an older one. I call it sort of, it was on the real QM, where it stands for real quantum mechanics based on geometry, electromagnetism, no strong force, no electroweak force, no weak force, and a toroidal electron model, a thin toroidal electron model, not a fat one. Thin, I mean really that point-like charge has a tiny size as compared to the interaction radius of the electron as a whole, which is the Compton radius. And so I just refer to that. You can go on my ResearchGate page, and it's from beginning of this month, and so I updated it today with an executive summary. And I want to show the context where I really analyze what what sort of the conventional development is. It's a series in a power series. The first order term is the first power is just alpha divided by pi, and the coefficient is 0.5. The second order term is one that you that has alpha squared divided by pi squared, alpha pi divided squared, and then a third order term, a third power, and fourth. So we develop these terms as well, but we get them really out of ordinary, geometry and electromagnetics. We've been accused of sort of doing our own model fitting. I think it's a totally irrelevant criticism. But yes, so I refer to this paper for really the details. I'll just go over the basics. The basics is this electron model, a ring current model. It's been around forever. There's always been an issue with the radiation. We have sort of a complicated but a real physics explanation of why this model does not come with the radiation problem, why it does not irradiate its energy out. That's a bit complicated. It comes with retarded field potentials. As the electron or the point-like charge goes around, it changes its dynamic electromagnetic field, and that travels to the other side where it then picks up its own radiation that was emitted a while ago. So two basic physical radii, the Compton's radius, I said, that's h bar divided by the mass of the electron as a whole times c, and then that small, said here it's shown out of proportion, alpha times that radius. So both are connected by that fine structure constant. So to highlight the differences between the mainstream quantum electrodynamic stories, I won't go too far in it, but that's where you see on the left bottom there a one loop, one virtual photon loop. I never got really into it, and you see an electron left, an electron right, or a charge, and then a virtual photon that gets exchanged. You have two loops. Virtual photon can apparently interact with itself and split and come together, and that leads to sort of that second order correction in mainstream quantum electrodynamics, the Peterman apparatus, lots of integrals. Third order is even more complicated, 72 virtual photon loops with thousands of integrals that have to be calculated. In our real quantum mechanics geometric story, I would say we arrive, I mean, there's a number of explanations and refinements, but we arrive at a very natural explanation for the alpha divided by 2 pi, basically saying that, we have a charge, which is point-like, but not indefinitely small. When that makes one loop, in the larger loop, I should return to the previous picture, it has some intrinsic spin. Each big loop that it makes also means that itself goes around its own axis once. So that creates a magnetic moment of its own, and that really adds that about 1% to the theoretical magnetic moment that you would get when calculating it from, assuming that the point-like charge that goes around and around and around has no size whatsoever. So the simple picture would be that, an electron, the point-like charge inside has like an electromagnetic aura or magnetic moment that spins with it. The second order corrections come from, as you have that, I'll explain, we need to do some velocity corrections. We get sort of a helical path for each discrete or infinitely small charge element within that point-like charge. And that, wise, I put here, it slows the orbit slightly. That makes sure that every charge or charge element inside of that point-like charge moves exactly at the velocity of light. So the electron weaves sort of an orbit. I'll show that. That's a toroidal model, slowing down as a whole just a little tiny bit. The third order corrections are a bit more complicated, and that has to do indeed with retarded fields effects and waves that collapse and bounce back when they hit sort of a wall. Have to watch out, of course, for credits of the visualization of these Feynman diagrams. The first one, the one-loop diagram, just comes from ResearchGate, but I think comes from Wikipedia, really. The second one, much more complicated, is from the bigthink.com site, which I didn't know, but it's a nice site. Where, yeah, these virtual photons mediate attraction and repulsion. I think that's a very medieval picture of how things might work. I mean, we spent like a century getting rid of the vacuum as thinking of it as being some kind of ether, and I feel, yeah, quantum electrodynamics after the Second World War reinvented that kind of picture of the vacuum as some kind of ether. So let me explain that little problem that we have. So again, we imagine this point-like charge. Said it's shown out of proportion here. It's alpha times the Compton radius, but it has a size. So if you think of that charge as either a shell of charge or a full sphere of charge, the charge elements that are outside of the pure theoretical motion of the point-like charge as a whole, they actually move at a velocity that is higher than light. How much larger? Well, that's just standard expression for orbital motion. It's c times 1 plus the radius of that point-like charge, alpha. So if you normalize the big radius, the Compton radius to 1, then we have alpha. And it's larger than c. And so that's a relativity violation because nothing can go faster than light, not even these, I mean, in art theory, because it seems logical, these charge elements inside that orange or yellowish, orangish point-like charge, they shouldn't be traveling faster than light. Of course, there's an effect that I said it rotates around its own axis as it makes a big loop, but still we have a problem there. Solving that problem actually solves the problem of the anomaly in the magnetic moment. Here it's not the best image. I asked DeepSeek to generate it. Again, it shows a helical path for these charge elements in the point-like charge as it spins around its own axis while making a big loop. So the proportions, this sub-frequency, I would say, isn't right, but it shows the idea. You arrive at what I call an effective radius for that point-like charge. Its distance from the center of the big loop at an effective velocity, which is given here. I refer to the paper for the calculations. Basically, relativistic dynamics. You won't add or subtract velocities linearly like you do in Galilean relativity. No, you will square them. So should go. The thing is, in the previous picture, actually, I said the effective velocity is a bit less than the speed of light. The effective radius is a bit less than the theoretical radius. So actually, you get a correction in alpha divided by pi, which is negative, and that was a huge problem for me in this geometry, where I didn't think about the self field that this spinning point-like charge generates. I just thought about the geometry and said, like, okay, this changes the geometric picture I have, and we should have a real measured magnetic moment that is less than the theoretical magnetic moment, while Schwinger's correction makes it more. And that's where field theory saves the day, as I put here. I said the spinning point-like charge generates its own little current, and it adds to the whole. It adds field momentum, and I give that field momentum there. It's what's referred to as the Abraham-Lorentz formula, which gives self-energy, self-mass, self-momentum of a sphere of charge with a coefficient 2 divided by 3, and then what you have there, a rather complicated fact, not too complicated, with the Coulomb factor in it, the square of the electric charge times the velocity of the motion of that charge. So the funny thing is really then that the Schwinger term re-emerges this time as a positive correction. So we've got sort of a baseline, that field momentum, that formula that I showed you, the loop geometry, vector alignment. I'll go to my paper because that's a bit of that's related to that Abraham-Lorentz formula, the energy if you put a charge together. Final result is really that you do get the first order correction, which is exactly Schwinger's correction, a measured or real magnetic moment. That should be the theoretical magnetic moment at Bohr magneton, times a power series 1 plus alpha over 2 pi, which I derive above, and then second order, third order corrections. So the field contribution really dominates the kinematic reduction, which I calculated as well. I said if the effective radius and the effective velocity of that point-like charge are a little bit smaller than the theoretical radius, and light speed, the kinematic reduction you would get in my model is actually a reduction of the magnetic moment of the order of alpha squared. So I get Schwinger's term, and then I get, just like the Peterman integrals, a negative correction, alpha squared divided by 2. But then I have other second order terms that I said are related to other field effects that this dynamic picture of the electron as an oscillation of charge yields. I think I'm almost done. It's a short presentation. We're under 20 minutes, which is nice. So that's really the conclusion. For the details, I really refer to that publication. It would take me hours to explain it here, or basically read off my paper, which I won't do. But if you really combine the three, and I focused too much on geometry in the past, but really the geometry, and then see what kind of fields that come with that geometry and those dynamics, and our relativity theory, you get at a common sense explanation of the anomaly in the magnetic moment of the electron. It's something I'm going to develop in, I'm thinking of rewriting a manuscript, because I said the concept of sort of a self-energy, really the nature of that naked charge, is very relevant also when we take it to proton models, neutron models, and explain what, if you watched previous presentations on these matrix mechanics approach to modeling, helium-4, more complicated models of nuclei, isotopes, naturally occurring elements. You get in those matrices sort of a self-energy, which is sort of the three-dimensional equivalent of the point-like charge inside of a proton, and then the two charges which we think of make up a neutron. So enjoy it, look at it. I triangulated this with ChatGPT, which in a previous presentation I said wasn't very much into this model, but now it's very enthusiastic. It understands the geometry and works now with DeepSeek and Gemini to wrap up loose ends like this. No virtual particles, no renormalization of very complex perturbation terms that don't converge, lead to infinities, no abstract probability waves, just geometry, relativity, and field theory. Basically the equations of motion, which Dirac referred to in the 1930s as the ultimate derivation of these equations of motion as the ultimate objective of quantum mechanics. I thank you, and I wish you a very nice afternoon. Especially, I hope you will enjoy the World Cup game between England and Argentina tonight.